Estamos aqui para ter mais um seminário de sistemas dinâmicos e hoje recebemos o Isaia Nisoli, da UFRJ, e o tema da palestra dele é A Computer Assisted Proof of Noise Induced Order.
So today I will speak about this joint work with. First of all, thank you for. I would like to thank him for giving me the opportunity of speaking. And today we speak about this result that I have with Stefano Galatolo and Monge. And there are many things that here that are not usually seen in a title. Okay, computer-assisted proof, it means that we use a rigorous form of computations to prove results, a result that is connected with a dynamical system. And the other thing is this noise-induced order. Okay, so let's start and introduce the problem. And I have a video. I have a video that is not working in the PDF, so I have put it here. So there is this chemical reaction that is called the Belosouv-Zhabotinsky reaction. And this chemical reaction is quite special in some way. It has a really interesting story. I will speak about it. And it is really special because up to the 50s, when Belosouv discovered this reaction, it was expected for a chemical reaction to always go towards a thermodynamical equilibrium. And at some point, Belosouv was a Russian chemician that was working on finding non-organic analogous of the Krebs cycle of cellular respiration, and he found this chemical reaction that is oscillating, and it oscillates as a nonlinear oscillator. And as a matter of fact, this was taken with some. It was not really trusted. He discovered this reaction in 1951. He tried to publish his results for many years, but essentially no editorial board trusted him. And so he finally published this result in a paid journal, and he left academics. He had a really complicated life history. He fled Russia after the revolution in 1905. He studied in Switzerland, got back after the October Revolution, started working in chemistry. So he was a really complicated. He had a really complicated life. But then his director in the laboratory gave to Zhabotinsky, who was a PhD student, this kind of oscillating reaction as his PhD thesis. And Zhabotinsky developed a whole theory of these oscillating reactions, and who have become a fundamental topic in theoretical chemistry up to now. And what happens is that this Belosouv-Zhabotinsky reaction have been studied a lot. They became known in the Western countries in 1968 at a conference, and a lot of effort in applied mathematics and physics and chemistry has been devoted to these reactions. And one of the things that happened is that they used time series to study these kind of reactions, and showed that these reactions have the time series associated to this reaction have a positive Lyapunov exponent that is considered an indicator of chaoticity. And when this reaction under controlled condition is has some sort of random noise added that could be a pump that is pumping some reagents with random pressure, or illumination, or illumination, then you have this phenomenon of excitability. So you have these patterns developing and this kind of special structures developing. And so there are many articles about the topic, especially in the world of applied mathematics. And as a matter of fact, there is this really nice study that is in chaos, deterministic chaos in the Belosouv-Zhabotinsky reaction, which speaks about various models for this reaction. And at some point, they speak about this return map that shows the potential of the brom ion at step n+1 in function of the minimum for the potential of this bromate ion at step n. And a couple of Japanese mathematicians, Matsumoto and Suda, they developed a one-dimensional model that is associated to this return map. And this model depends on 3 parameters, and these 3 parameters are such that this parameter A is such that the derivative at 0.3 is equal to 0. This parameter C is such that the 2 branches of the map, they glue together well. And this parameter B, I will give an explanation now. I will need to show that on the blackboard because it has connection with the Mishurevitz parameters. Okay, so the idea of Matsumoto and Suda was to show in this was to take this parameter, study its perturbation, its random perturbation, and see if they could show this transition from positive Lyapunov exponent to negative Lyapunov exponent. As you can see, the Matsumoto-Tsuda map, as her profile is really similar to the one-dimensional return map, and so to ensure that they wanted to have some hypothetical reason for which this map with small noise, with a small amount of noise, should have positive Lyapunov exponent. And so their idea was the following, which justifies this B, is they took the map, the Matsumoto-Tsuda map, and it has a fixed point, and this parameter B is such that the critical points end up into this repelling fixed point in 4 iterates. Okay, so it's a kind of Mishurevitz condition. It's like in the unimodal map, you call Mishurevitz parameter when the critical points end up in a repelling fixed point, and here the idea behind this B was exactly this. What we are going to study is not the deterministic system. It's not this underlying deterministic system. But what we are going to study is the random dynamical system with noise, okay? Associated, that is driven by this map. So, as a matter of fact, when Matsumoto and Tsuda found this map, they did a lot of numerical studies about this map, and they showed that in their numerical studies, they just iterated the map many times, added some random noise, computed the Lyapunov exponent from the time series that were generated by the computer. They showed this transition from positive Lyapunov exponent to negative Lyapunov exponent, but what happened is that this is not a mathematical proof. So because the simulated map may have nothing to do with the real dynamical system, and this transition could be a numerical artifact. So, and from that time, that is around I think it's 1981. I forgot to put it here. There have been many tries to prove this this noise-induced order, this transition from positive Lyapunov exponent when the noise is small to negative Lyapunov exponent when the noise is big. And there is a paper by Doi which shows the existence of this noise-induced order in a piecewise linear map. And what happened is that while we were at this school at Trieste, we heard a talk from Yuzuru Sato about this phenomena, and we thought, okay, maybe we could apply to this phenomenon, to the study of this phenomenon, the techniques of our techniques of approximation of invariant measures. The model by Doi is in some way is a more complex version of this model. So imagine that you have a tent map here, and when you look at the dynamics on the tent map, the Lyapunov exponent is positive, and when you add noise, your system starts to visit with positive probability this set where the dynamic is constant, and so you have a transition from positive Lyapunov exponent to negative Lyapunov exponent. Essentially, this is the idea behind the model by Doi, and is more or less the idea of what happens also in our system. Okay, but from the idea to prove that there are some non-trivial intermediary steps. And so what we do is that we study this dynamical system with noise, with additive noise. And
sorry, Pujas has a question. He's asking about what happens. In fact,
falar em português.
The transition happens when the size of the noise is increasing?
Yes.
Yeah, that's the first question. What's the parameter to which is referred the transition?
What's the parameter?
It's referring to the transition.
So if we can find exactly the parameter where we have the transition. So what we can do is that we can compute the Lyapunov exponent for many different values of the noise. I can show, like these are different. These are the Lyapunov exponents for different values of the noise. Clearly, there are some, I will come back to this, but it is possible, in some way, it is possible to find a way to certificate in which interval is the transition. But this is something that you have to do. It is a process that you have. So finding the parameter where you have the transition is non-trivial, and you have to develop a technique to do that. Okay?
There is a third question. How is that related to the initial problem?
How it is that related to the initial problem? So to the initial problem of the Belosouv-Zhabotinsky. So what happens is that in the initial, when you have the chemical reaction and you had a small amount of noise, when looking at the time series, you can compute the Lyapunov exponent of the time series and see that this Lyapunov exponent is positive. Okay, when you add enough noise, you will compute for the same time series, the Lyapunov exponent. You see that this Lyapunov exponent is negative. So it is postulated, this is chemistry and physics, that this transition from positive Lyapunov exponent to negative Lyapunov exponent is exactly the things that builds up these patterns, more or less. Ask him if he is satisfied. But okay, but so the idea is to study this system and to use this analytic theory of invariant measure to study this system. And so into this game, enter two things enter into play, and these two things are the transfer operator, which is an operator that acts on the space of measures that generalize the action of the dynamics. And this operator, which is the convolution by the noise. Okay, I will try to give an intuition of what is the transfer operator and of what is and why we convolute with the noise after that. And the idea is that if we take the interval 0, 1, so let's start with the fact the transfer operator is an extension of the dynamics to the space of measure. So what happens when you apply the transfer operator to a Dirac delta? So if you apply the transfer operator to the Dirac delta in the point x, then you will see that the image through the transfer operator of the Dirac delta at the point x is the Dirac delta at the point t of x. So we can think that the transfer operator takes, if you take a density that is essentially we think of points as sand, so as a density of probability as sand on the interval 0, 1, and we let the transfer operator act, and we see how this sand is spread out through the dynamics. Okay, so when the dynamic acts, the sand is spread out, and when we add some random noise, what happens is that at each point we are convoluting essentially each point. If you think about the Dirac delta, you're sending a point to the image of the point x to the delta in the image of the point x, and then what you're doing, then you're adding a random noise. So the probability distribution, so the density of the distribution of the points after one step of the dynamic plus the error is exactly the error centered at the point t of x. And this operation is exactly doing the convolution of the noise kernel with the transfer operator. And this is a really interesting thing. Why? Because the dynamic, as you can see, the deterministic dynamic, the underlying deterministic dynamic, it's ugly. So it's not ugly, but it has some really difficult issues. So the underlying deterministic dynamic has a point where the derivative is 0, and it has a point where the derivative is infinity. Okay. Moreover, we wanted to prove that the noise-induced order was we wanted to prove the noise-induced order for the parameters of Matsumoto and Tsuda, and this adds another level of difficulty because there are some results about maps with a critical point and a singular point, and there are results about constructing towers and about proving that they have positive Lyapunov exponent. There exists an ACM, but in general they depend on estimating the size of the tail and proving that the tail as the size of the tail decays with the exponential size. Moreover, here we have explicit parameters. And another issue is that, in principle, proving that the underlying deterministic system has positive Lyapunov exponent is not enough. Why? We want to prove that the dynamical system with a small noise has a positive Lyapunov exponent. So in some way, we should prove that the underlying dynamic has positive Lyapunov exponent, but the stochastic stability of the underlying dynamical system. So this adds a lot of difficulties to the problem. But in some way, if we look at the thing by looking at the functional analytic viewpoint, and we look at this convolution, convolution gives us a lot of help. Why? Because this is something. If you have done some courses in functional analysis, one thing that you learn is that when you convolute a kernel with a function, then the convolution has the same regularity as the kernel. So if you take a bounded variation kernel, the density that you get from by applying the operator LC, where C is the size of the noise, has at least the same regularity as the kernel. And since if you choose a BV kernel, then what happens is that this operator LXC is preserving the BV space. And since it is preserving the space of bounded variation, then you can find a fixed point inside the space of bounded variation, and this permits you to apply these techniques of approximation of invariant measures. So the results that we get, the result we get is the following. If you take the Lyapunov exponent of the system with noise of size, let lambda xc be the Lyapunov exponent of the system with noise of size xc. This is defined as the integral of the logarithm of the derivative with respect to the stationary measure of the system with noise. We have that this Lyapunov exponent is Lipschitz in xc. And if you take a small noise, which is this one, and you take a big noise, that is one, then you see that, okay, for the small noise, the Lyapunov exponent is positive, is rigorously certified to be positive. And if for a small noise, for a big noise, the Lyapunov exponent is rigorously certified to be negative. Okay? And these are the computed Lyapunov exponent. And one of the first questions that usually comes to mind when you look at this graph is, okay, these are all points. And we know that they are Lipschitz, but is it possible to, you said that the Lyapunov exponent is Lipschitz with respect to the noise. Can you say something more about the regularity of this exponent? And what we prove is that that the Lyapunov exponent is Lipschitz with respect to the noise, and is also Lipschitz with respect to all the parameters. Okay, is Lipschitz with respect B and with the parameter B and C, and with respect to the parameter A, since it is changing since the parameter A is keeping track of the derivative at the critical point, then we only get that the Lyapunov exponent has regularity A log A with respect to this point. So what's the strategy? We take a noise, okay, and we discretize the operator, this operator LXC. It is regularizing, so it has really good properties using the Ulam approximation. Using this Ulam approximation, we find an approximation of the stationary measure, of the density of the stationary measure with an explicit bound. And using this and some more knowledge of the regularity of this stationary measure, then we can compute these Lyapunov exponents. Okay, this is the strategy. And the most important thing is to speak about what is the Ulam approximation. The Ulam approximation is a really natural way of approximating dynamical systems, and it is the following. So you take you have a projection from the space of segment measure into L1, that you take a partition of 0, 1. In intervals of size delta. So you take 0, 1, you divide it in a homogeneous interval of size delta. And what you do is that you look at the conditional expectation of this measure on these intervals. So if the measure has a density, what you do is that you're looking at a piecewise constant function that represents the average of this density on each interval. And what happens is that if you look at if you discretize the transfer operator by by using this projection, what you get is the following. You get a matrix. If you look at it on the basis of the characteristic functions of the, and the entries of this matrix are nothing else than this. So you take your intervals, and the entries of this matrix that you get by discretizing the transfer operator are nothing else than the conditional probabilities of getting from interval ij into interval I1. And so this is nothing else than a Markov chain. It's a finite state Markov chain that is approximating your dynamical system. Now, if you look at the fact that this Markov chain approximates your dynamical system is a delicate issue, usually. And this Markov chain approximates your dynamical system when you have some regularization properties. So in general, this Ulam approximation of the operator L, for this dynamics, in principle may not approximate really well the dynamical system. But if you look at the discretization of the operator with the convolution with noise, then we get all these good regularization properties, and this discretized operator approximates the operator with noise. Okay. So these are essentially the fact that the convolution operator has good properties is essentially contained in these inequalities. And I think the most important of those is this one. You can see that the convolution operator is bounded from L1 into variation. So essentially, it takes it takes a density in L1 and returns something that is in bounded variation. And this is exactly the idea when I'm saying that the operator is regularizing. This is exactly the idea. Moreover, you can see here that the operator NC is well behaved with respect to the projection. And I think it is interesting to see here that the size of that in some way the size of the noise, to get a good approximation, the size of the noise and the size of the approximation have to be the size of the approximation must be small compared to the size of the noise. Okay, and there is one of the biggest issue when you do this kind of approximation is that when you're dealing with the Markov chains, a delicate issue is to understand how long time it does take to them to mix, because in some way how fast you reach your fixed point is determined by how fast these Markov chains are mixing, or the original operator are mixing. And what we do is that we instead, there are this idea behind the approximation of invariant measures is it has been there have been many people working on this idea since the 90s, and one of the issues was exactly try to estimate the mixing time a priori, the mixing time of this discretized operator a priori. And in some way we resolved this issue by developing a technique a posteriori. Instead of trying to estimate the mixing time of the operator a priori by analytical estimate or something like this, what we do is that we discretize our operator, and then we put the computer to test this operator. So we test the mixing time. We find essentially we let the computer rigorously compute the time, an n and an alpha, such that the action of the discretized operator on the space of zero average functions of zero average densities is smaller than a number smaller than 1. Okay, so we start to iterate on the space of average zero densities, and we wait. Okay, we let the computer iterate these vectors. We have rigorous bounds on the error of the operation of the computer. We have rigorous bounds on everything, and then at some point we see that our discretized operator, after n steps, it has contracted the space of average zero BV densities up to 1/2. Okay, when we have proved that this has computed up to 1/2, then we can apply this simple inequality, and we can show that the distance between the density of the system with noise and the stationary density of the system with noise and our computed stationary density is bounded. Okay, it is bounded by this difference between the iterations of the discretized operator and the non-discretized operator, and that this difference can be bound using bounds on the norms of the norm of the discretized operator. Okay, this so you can see that this is the discretized operator, and this lambda is usually can be or the original operator or a finer discretization of our discretized operator. And these secant I are these bounds on the norm of the discretized operator on the spaces of average zero densities.
So the main point in the assistance of the computer is the fact that these L1 norms are uniformly bound for delta and pc.
Yes. You can, yes, you can. As a matter of fact, you can find, okay, fixed at C, fixed at delta, you can bound these L1 norms, okay? And you get this CI, okay? Once you have fixed this CI, once you have fixed delta in C, you can estimate the norm of the stationary operator. And moreover, you can say, okay, if I compute the stationary measure for the Markov chain that is approximating my system, then it's going to be near the stationary measure for my original system with noise. Okay. So there is a philosophical principle behind this. In some way, this happens when you have piecewise expanding maps of the interval, and when you have this regularizing action of the noise kernel. That in the case of the noise kernel, what you expect is that since you have this noise kernel acting, more or less all the things that are much smaller than the noise, so you can think about that. The kernel of the Ulam discretization are functions that have average zero on each. So the kernel of the Ulam discretization are function of this type, or something like this. So they have average zero on each element of the partition. Okay. So what happens that if the size of the partition is much smaller than the noise, and since the noise is regularizing, essentially all the things that you are saying are more or less of the size of the noise. Okay, you are comparable with the size of the noise. Things that are oscillating a lot in small intervals of the partition, they are not going to influence so much the behavior of your system. Okay, and this happens also when you have piecewise expanding maps of the interval, because at each step these things that are in the kernel of the projections, they are split up. So in one step, you will see that they will become suppose something like this. And then at some point, since the system is expanding, these functions that were in the kernel of the discretization became visible to the discretization after some iteration of the original system. So playing a game by iterating for some steps the original system and then iterating the discretized system, you can find a way to see the behavior. You can control the behavior of all the functions in BV. Okay? And so this kind of inequality, we call it for coarse fine. Why? Because exactly because they give us a more or less uniform estimate for the operator associated to the random dynamical system and for the discretized operator with the refining partition. They permit us to estimate. So the most computationally expensive part of this work is exactly to estimate this secant I. So you can imagine you have a huge matrix. It's maybe 1 million by 1 million or 20 million by 20 million. And you have to compute its action on a space which is 20 million minus 1, 20 million minus 1, which is the space of average 0 BV densities. Okay? When you apply the discretized operator, it is acting on a space which is n minus 1. And so you have to compute a lot of matrix vector multiplications. And so what we do is that we compute this for a smaller partition, and then since we have these coarse fine inequalities, we can bring this information that we have from the coarse partition to a finer partition, and so get much more information. Okay. And moreover, this information also tells us that if the discretizing operator is contracting in L1, also the original operator is contracting in L1. And this is quite important because, as a matter of fact, I was cheating in some moment. And this is quite important because, okay, we know that since the original operator is contracting in L1 and we have these bounds with the noise that say that it is bound from L1 to BV, this means that it also contracts BV. Okay? And this means that if you have a stationary measure, okay, the stationary measure has density in BV. Okay? But not only that. Since it is contracting L1 and BV, this stationary measure is unique, and so it is ergodic. And so when we speak about so this definition of the Lyapunov exponent makes sense. Because in principle, this Lyapunov exponent with respect to the stationary measure may not, in principle, the stationary measure may not be ergodic. And so not only our a posteriori estimate permits us to approximate our invariant measure, but it also tells us that the original random dynamical system is ergodic. And so the coarse fine So as a matter of fact, the article is kind of it has a lot of mathematics inside because there are many issues devoted to treating this kind of approximation, and this is not only the mathematics is complicated, but also the computational part is kind of complicated. So under the hood, there are many things. We have the contraction time is computed on using GPU multiplication. So you have to, and we use some bootstrap methods and something that we call local Lazotte-York inequalities to ensure that the density that we get is regular enough to do our estimations. So we have 2 points. We have a point where the derivative is 0, And so there the logarithm of the derivative explodes, and we have a point where the derivative is infinite. So also there the logarithm of the derivative explodes. So we have to check that the density is not too big into these two intervals that contains the 2 points. And so there are some bootstrap arguments that permits us to get a first discretization of a first approximation of the invariant measure, and then use this approximation to get better estimate for a new approximation by using these Lazotte-York arguments, and these are the approximated densities. So this is the approximated density for the small error, and this is the approximated density of the stationary measure for the bigger error. And you can see that in this case, the system essentially does not pass too much time here, where in the contracting branch. And if you look at if the error is much bigger, then you have the system is starting to pass a lot more time in the contracting branch. And this is the reason why we get this negative Lyapunov exponent. And okay, the paper. So all the paper, the technique was developed to treat this noise-induced order problem, but all the technique passes to is axiomatical. So it generally works with it works for general system with additive noise. So you could use that for any system with additive noise, and everything can be adapted to other noise kernels. And also the Lipschitz argument that permits us to prove that the Lyapunov exponent is Lipschitz passes to is axiomatical. So it passes. There are no problems in adapting that to other maps. Now, one thing that I would not that I want to stress is that we didn't treat in any form the underlying dynamical system. So the underlying dynamical system, what we discover, the information that we get about the Lyapunov exponent, and it depends on the noise. And in principle, it may have nothing to do with the original dynamical system, with the underlying dynamical system. Why? Because for it to have something to do with the underlying dynamical system, we have to prove stochastic stability. And stochastic stability, in general, in the case of unimodal maps, is not easily proved. There is a proof of stochastic stability for unimodal maps, I think for the logistic family by Baladi and Viana. And there is no proof of stochastic stability for a map of this type, at least that I know. And so to prove to prove the properties of the original map, of the underlying map, and to prove stochastic stability is a lot of work, and it involves a lot of probably it's possible to prove a Jacobson type theorem for this kind of map. I think there are some, probably you need to have some computer-aided assisted estimates, because the behavior of because you have a lot of, if you want to prove a Jacobson type theorem, you have to control the distortion and have a really fine control of the size of the derivative. So I think it's probably something quite complicated, and proving also the stochastic stability of this system is probably something complicated. Yeah. So that's it.
Questions and comments? Pujaus has one more question. Given axiom A such that all the attractors are periodic attracting points, and if the noise is sufficiently larger, would the result be the same?
I think that Probably yes. So essentially the noise is bringing the dynamics into pieces of the space where you have contracting behavior that are seldom visited. So if you have pieces of the dynamic that are seldom visited, and if you add enough noise, then you would visit them with positive probability, and you would get a negative Lyapunov exponent.
He continues, meaning that the Lyapunov exponent is negative for some noises? Meaning that the Lyapunov exponent is negative?
For some noise?
Yeah.
Yes, I think so.
Or even in the case there are some non-trivial hyperbolic attractors?
I don't know. I think that I think that so suppose that you have an attractor, okay, and you have a ball inside which you have. The question here is kind of delicate because here you have that the system with small noise has positive Lyapunov exponent, and that in some way that iterating also the Lebesgue measure. So if you take a system which is a kind of product, so if you can split up your system, it's easier to build up such kind of example. So if you have imagine that you have a ball that contains a horseshoe or something that has a positive Lyapunov exponent, and while you stay into this ball and outside you have a lot of periodic sinks, and if you add enough noise at some point, even if inside here you stay inside here all the time, at some point if you add enough noise you're going to visit these sinks with positive probability, and this is going to give you a negative Lyapunov exponent.
More questions or comments? I think we can thanks the